All right. So I wanted to talk to you guys about maybe one or two more reactions out of the Amines chapter here. And the first one I wanted to talk to you guys about is kind of well, let's say we're building upon some older knowledge, I guess. So let's say that we have a ketone, and it doesn't really matter what it is for this case. We'll just give that ketone there. If I take this ketone and I react it with some ammonia in the presence of some kind of catalytic acid, not the p-toluene sulfonic acid, some kind of organic soluble acid there, right? If we do this, we'll end up doing a Schiff base, right, which we talked about in the carbonyl chapter, right? And we end up making an imine, right? IMINE, right? So an imine. And, that's a useful mechanism to know, right? We have an acid, we have a good nucleophile, we protonate the ketone, we bring in the ammonia, blah, 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 right? So hopefully you guys can figure out the mechanism to get from one to the other, right? Check your notes, or I think, was this? No. I think that was a reaction that we did while we were still in person doing classes. So it should be in your notes. I don't think it's in one of the videos that I have for you guys. Great. But anyway, so if we take that imine, and we react it with this reagent here. So NaBH3CN, okay? So sodium cyanoborohydride, okay? So sodium cyanoborohydride. If we do that, what we end up doing, very useful, is we end up taking an imine to the ammonia, oh my goodness, not the ammonia, to the amine. So this is the hardest part about this chapter for me. I always amine, amide, ammonia. I get tripped up sometimes with the verbiage there. Anyway, so imine to amine. So sodium cyanoborohydride, right? This is just a cousin to sodium borohydride. Right? And if you remember, sodium borohydride was useful as a selective reagent for reductions of certain carbonyl groups, right? And what's useful, as soon as we swap, right, that cyano for one of the hydrides there, right, we change the reactivity of this, right? I don't want to say decrease the reactivity, although that would be a fair statement to make. Right? We just change the reactivity so that this reagent is fairly selective towards reduction of imines. I'm not saying it won't react with other stuff, right? I'm not saying it won't react with other stuff, but it will selectively go after an imine over a ketone, okay? So this is a very useful reagent for us to have to be able to turn a ketone, right, directly into an amine, right? And we can kind of combine this into a two-step process, so to speak, right? We can put those two together there, all right? So that's useful for us because we talked a lot about how to generate a ketone, how to oxidize them, how to reduce them, how to put them here, right? In the last chapter, we talked about, what else we can do with them, right? We can talk about, we talked about alpha alkylations and halogenations and all this, right? So we talked a lot about what to do with carbonyls, right? And here's just kind of another useful part to them, right? We can turn them into an amine now just by using ammonia, some acid, and that sodium cyanoborohydride there, okay? So that's pretty darn useful for us, okay? The next set of reactions that I wanted to talk about is kind of, so I kind of struggle a little bit with what I wanted to do with this video. And now my computer's not scrolling. I struggle what I want to do with this video, whether I wanted to show you guys all this mechanisms that are coming from this or not. I've decided not to. The reason why is because, whenever I kind of decide what I want to do with a mechanism for you guys, it's, is this mechanism useful in another set of reactions? Are we going to see this somewhere else? So we don't really see this somewhere else that much. So, and given it's near the end of the semester and it's been a weird semester too, hey, why the heck not, right? So, I will post a link that talks about the mechanism, and it's in your book, of course, right? But this isn't a mechanism I necessarily expect you guys to be able to apply somewhere else, right? With respect to what we have. All right. So now let's do this, right? So let's say that we've got our good old buddy Mr. Aniline, right? There we go, right? Hopefully you guys know how to make that amine, right? We are going to be living in the world of aromatics, okay? So what I'm about to show you guys is well, I got to be careful here. For our purposes, this will only work with aromatics, okay? But you'll see why in just a minute, why this is super duper duper useful, okay? But anyway, so once we have an amine on an aromatic ring, if I take that amine and I put in some sodium nitrite and hydrochloric acid, okay? If I take those together, I make sodium nitrite and hydrochloric acid, right? What I can do is I can take my amine and I turn it into something called well, I'll just draw it out for you guys. Okay. I turn it into this. And for completionist sake, which is very important, right? We've got a chloride ion sitting around there too, okay? So we gotta go, oh my goodness. Okay, let's pause here and take a quick peek, okay? So what in the world did we do? Well, this is the mechanism from to how this turns an amine into that, let me give you guys a name, diazonium. Okay, this is a diazonium salt, right? A salt just because, right, it's got a positive negative part too, right? So this is a diazonium salt. Now, immediately you guys should take a look at this group. Let me get yellow's fine, right? Immediately you guys should take a look at that group and go, that is a fantastic leaving group, right? That is a fantastic leaving group. It's got a positive charge, right? So when that leaves, right, when that leaves, it's going to leave as a neutral group. That's a fantastic leaving group. And it's also going to leave and kick off N2. And that's what makes this such a useful reaction or set of reactions we're about to learn. Right? Generating that diazonium salt, we can do a lot with that, right? We can do a lot with that. Okay? And so it's that green group right there is just going to be useful to swapping out for different groups here, okay? So let me take my diazonium salt, okay? I'm just bringing that down here. I need some space. Boom, right? So let's do maybe the obvious first. Let's do Cu, I'll do CuCl, CuBr, CuI, okay? If I take my diazonium salt and I put it with copper 1 chloride, copper 1 bromide, copper 1 iodide, what I'm going to just end up doing, right, is in all three of these cases, I am going to end up swapping in a chlorine, a bromine, and an iodine respectively, okay? And say, well, okay, that's nice. Chlorine and bromine, those aren't too hard, right? We can do our Friedel-Crafts, we can do our halogenation with our Lewis acids, right? Iodide's a little bit weird, although we could do it another way also. But remember, the point is this, right? The point is we start with an amine, right, that we turn into the diazonium and then transform that into a halide, right? So effectively, we get rid of an amine and we swap it in with a halide. Okay, so don't forget about that, right? It's not so important that, I can put a halide on the aromatic ring. Like, we already know how to do that. What we're doing now is transforming an amine into one of those groups, okay? A couple of quick comments here. Maybe not comments, but just this and that. We could also just use something as simple as potassium iodide. That would swap that in, right? We have to be careful of what solvent we use in some of these cases, but that's, a different argument, I guess, for a different day. We can also, related, right? Copper 1 cyanide. That will let us swap in a cyano group. Green, here we go. Oh no, I'm running out of room. Right, that can let us swap in a cyano group. And remember, we can do a lot with cyanos, right? We can turn them into carbonyls. We can, reduce them and all this other, right? We can reduce them, turn them into amines, right? We can do some Grignard reactions. That's everybody's favorite, right? So remember, we can do a lot with cyanos. So cyanos are very useful functional groups too. But we can add those pretty easily if we just put some copper 1 cyanide in there, okay? All right. Keeping on here, I'm saving the best for last. And I know you guys can't see it, but I'm putting heavy air quotes around best. Oh boy, I can feel the anticipation. All right. So moving away from the copper stuff, H3PO4, okay? So some phosphoric acid. I haven't seen that too often, right? We've used it in some dehydration reactions. Let's go to something a little bit more familiar with us. A very rarely used acid, sulfuric acid there. Just kidding, of course, right? And we'll heat that up. All right. Cool. Let's talk about these two real quick then. If I take phosphoric acid and I drop that in, I end up swapping my diazo there for a hydrogen. Very useful, right? Very useful. Because again, right, I'm just going to draw it in here for emphasis sake so you guys get the point of what we're doing, right? I know you guys are with me, right? I'm not being condescending, right? Remember we said with amine to the diazonium into a hydrogen, right? And so we got to think about what this means, right? Or what this means. Oh gosh. All right, I'm sorry. So what this means is, right, if we think about comparing these two compounds here, right? Just broadly speaking, right? If we take a look at the one on top there, right, we've got that aniline, we've got that nitrogen attached to that ring. So that's an activated aromatic ring, right? And so we have to pay attention to what it's going to react with. It's going to react multiple times, blah, 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 right? Amines are basic, so we have to be careful of what we put in there as we're trying to react stuff, right? But being able to swap out an amine for that hydrogen there is really, really darn useful, right? We get rid of an amine. We don't have an activated ring anymore in this case. There's these other considerations to have with that, right? I think you guys get the point, right? Sulfuric acid, water, all this kind of stuff. Here's something very useful. Now we turn it into an OH. Okay, so really the only way that we've learned how to add a hydroxide directly to the ring was through maybe some kind of nucleophilic aromatic substitution, right? We could do it that way. But here we have a way of adding a hydroxide to that. A little bit of, I don't know, if controversy is the word we want to use here. Here's the thing. Let me take a brief aside here. So just for a little bit of a behind-the-scenes look, when I go to pick a book for you guys for this course, or when any professor goes to pick a book, right? The reactions that they show you here in the Wade book are going to be a little bit different than what you might find in a different book. And if you look online, there's subtle differences here and there. And the whole point being this, right? There's more than one way to skin a cat, as the saying goes, right? To turn the diazonium salt into a hydroxide, some books say sulfuric acid and water and heat. Some just say, right? Some just say water and heat, and their answer is yes, okay? So the point being that, there's different ways of doing this, and when I say something generic like heat, like how much heat? Like 100 degrees Celsius under pressure, maybe. So it doesn't really matter too much, right? You put some water in there. That those diazoniums are such good leaving groups that we're able to pretty easily kind of swap those out for something. Okay. All right. Let's go for the showstopper. This is what you guys have been waiting for. Okay. So I'm going to put it in purple here because this is pretty darn important. Okay. because I think, okay, this is going to be the first reaction, I believe the first reaction that we have learned in this semester, in this entire year, where we can add a fluorine group, right? We can add a fluorine group to anything, pretty much, right? We really haven't talked too much about fluorine, but here it is. If you can generate a diazonium salt, you put HBF4, okay, HBF4, which is a very, very strong acid, okay, very strong acid. You will be able to plop a fluorine directly onto that aromatic ring. Who cares, right? Well, remember, what did we say was so special about putting fluorides on our rings? Well, remember, now we've got a very good leaving group for the aromatic substitution, right? So being able to put a fluorine in there makes a very good leaving group for aromatic substitution onto our ring. So it can be very useful for us to do that. And on the more practical side of things, right, and if you didn't get the point of what I made earlier, right, this is a pretty rare for us to learn and a pretty rare reaction to happen, right? So being able to add a fluorine anywhere is a very useful thing to have, okay? And I can tell. I know I can't see you guys, and I know I can't really hear you guys, but I can tell that you guys are impressed. You said, wow, we can do whatever we want to with these diazonium salts. Yeah, that's kind of the point, right? They're extremely versatile groups, but they've got limitations, okay? These diazonium salts, we can really only do all this chemistry on an aromatic ring, right? If we try to do this on an alkyl chain, this is such a good leaving group, right? Let me, yellow here, right? This is such a good leaving group that it's just going to leave and form a carbocation and then do whatever carbocations do. Which, to be fair, right? Which, to be fair, might not be a bad thing. So I'm not saying we can't generate them on an alkyl chain, right? I'm not saying we can't generate them on an alkyl chain. I'm saying we really can't stop them and isolate them, right? They're going to immediately turn into a carbocation, okay? So it's a possibility, right? Just for argument's sake, right? Just for argument's sake, and I hope you guys aren't just skipping so that you just see this and you know, miss the rest of the explanation, right? If I do this, right? If I do this to an alkyl chain, yeah, I will generate a diazonium salt, okay? But that's going to leave immediately, right? It's really hard to isolate that, right? We're going to lose the nitrogen off of there very quickly, right? We end up with a positive charge. You know, we might have some chlorines around. We got all this other stuff, you know, so we end up generating a carbocation very, very easily this way, okay? So, if we were going on to a third semester of organic, we'd come back and we'd look at these reactions a little bit more. There are some, let's say, alterations that we could make to make this a little bit more useful for us, but not really something we're going to talk about in this semester, okay? So just pay attention that really when we're using these diazoniums, we're kind of limiting it to aromatics, but limiting is not a negative thing here, right? Okay, so there it is. That is essentially the end of the amines chapter 2. There's a couple other miscellaneous reactions here and there, but I think this will give us a good base that we can use amines with. All right. Okay, I will see you guys in the next video.